Good morning.
Morning. Good morning.
How's everybody today?
Fine.
Um, okay. Okay, guys, I think you should know that this Friday, coming Friday, is almost bank holiday in Ireland, so there'll be no, everything will be closed as if we have everything open. But, even without the lockdown, but all colleges normally are closed and all activities are off, all government activities. And also Monday is a bank holiday, so you have a long weekend, but you can't travel. They've also, just to let you know, they've enacted the law of travel here in Ireland. If you come from one of 32 countries that Ireland considers to have a lot of corona, so when you come back, you must spend 2 weeks mandatory in a hotel, and it costs about 1,800 euros. Cost you. So be careful if you do any travel. If you come back to fly from check those countries that Ireland considers one of those countries. If you come from one of those countries, or if you have traveled to one of those countries in the last, when you arrive to Ireland, it doesn't matter whether you have a corona test or not, you still have to spend 2 weeks mandatory in accommodation, lockdown, in a hotel. Many people don't mind if they have their laptop, they can still continue, but it costs you 1,800 euros. So if you are prepared for that, that's fine. Otherwise, don't travel. My advice. Okay. Okay. Right. Okay. Let's carry on with our topic. So we started looking at matrices, and we done the matrix operation, and we went on to generate an inverse of a matrix. So that's all fine, all in preparation to be able to encrypt using matrices. And to encrypt using matrices, we encrypt, say, a message written in English. So English has 26 characters. So we give every character a numerical value from 0 to 25. So as well as having the matrix operation that we can multiply our message into a matrix and then also multiply the ciphered message into the inverse of that matrix. Now that matrix has to operate on numbers that are no higher than 25. And therefore, we need to also work out what the inverse of a matrix. First, we get the matrix on modulus 26, based on the modulo or modulus 26. If we are using 26 characters, if our language is more than 26, 28, or 30 characters, then we'll have to work on a different modulus. But it's not just enough to get the matrix, but we have to get the matrix based on the modulus 26. And also the inverse has to be based on the modulus 26. So and that's what we will be doing. So if anybody doesn't remember what the modulus is, it's the modulo operation. So if you have any number like bigger than 26, if we divide it by 26 and take the remainder, so it's the modulo operation, the division operation, that you divide and take the remainder. So in reality, we are not changing the matrix, but we have the matrix, all the numbers reduced to values less than 26 with the modulo there. As long as we know this is a modulus, then it should be fine. So let me share the same notes if we are still there. Okay, so we got this far last week. We are able to work out the inverse of a matrix, possibly one of the best ways to do it, or the easiest as far as for me, but it'll be up to you to use any technique you've been given. But I find this technique is the easiest for me to calculate the determinant and then find the conjugate of the matrix and multiply the determinant into it, and we get the inverse of a matrix. So there are ample of ways or different ways. We looked at least 2 or 3 methods to find out the determinant and the inverse of a matrix. So we'll go straight to assuming we know how to find out the inverse of a matrix, and we go and see what Hill cipher, how does it work? We need to know how Hill cipher operates. So Hill cipher, first it's based on matrix operation. So it takes a message, say if it's in English characters, we give the numerical values of those characters. In English, there's 26 characters, so they're given numbers from 0 to 25, as we did maybe with Caesar's algorithm and all the other algorithms that we've used. And then we take the matrix, make sure it's modulus 26 and multiply it to this values. And if it gives us any numbers bigger than 26, they are adjusted to modulus 26. And then we convert them into characters and we send them. That will be our ciphered message. And then if we're gonna bring it back, we have to calculate the inverse of that message and then multiply it into the ciphered message. So the point is everything is based on mod or modulus 26. So we need to find out, we need to convert the matrix to 26 modulus and the inverse of a matrix over 26. So they could be 2 different values. They ultimately they give almost the same result, but if we use the modulus inverse of a matrix, then the results it will give us, they'll all be on modulus. They'll all be less than 20, the number 26. So this is not directly related actually to the matrix. Anybody knows what the result of this calculation? You all know how to, you all know how computers do calculations. Anybody knows what is the result of this calculation?
24?
24 can be right number, yeah, can be the correct result. How did you reach 24? What are the rules for computer calculations, arithmetic calculations?
In this one, left to right, first we will divide 60 with 5.
What's the first thing that a computer or a calculator would actually calculate here?
First is the one in parentheses.
Yeah, the ones, guys, the ones in brackets come in first. It's done first, has a priority. The ones with the power has a priority, and then division and multiplication, and then addition and subtraction. This is the order. And if they have 2 similar operations, like a multiplication and division on the same line, they go from left to right. That's the general rule. So I don't know how did you reach 24? Did you first resolute the 7 minus 5? That's 2. And then did you divide 60 divided by 5 and then multiply it into 2? Or did you multiply 5 into 2 and then divide 60 divided by 10? Remember, there are 2 ways to do this. You either parentheses, they always are done first. So 7 minus 5 is 2. So you have a 2 here. So do you multiply 5 into 2? Or do you first divide 60 divide by 5, which is 12, multiplied by 2 to give you 24, or 60. Before you do that division, you finish, you get rid of the brackets altogether. So you have 2 here, 5 times 2 is 10. So 60 divided by 10 is 6. So be very careful, find out the correct operation. If you have a calculator, you do it. Calculators are programmed to do it correctly. Also, a computer would, perform the right calculation. Try Excel sheets will give you the correct calculation, but be careful. Right, I'm gonna go to the next one. So now we do the modulus calculation. Again, just to make sure, I know everybody is quite familiar with this, especially if you've done any programming, you probably know because we use this a lot in programming. So 80 mod 26, that's dividing 80 by 26, the result is 3, and the remainder is 2. So 2, and if we have the alphabet, A is 0, B is 1, C is 2, D all the way to 25, then that will be the character C, that's what we refer to. So if we do have a number, whatever it is, number 3, if you have any, like if you get any remainder, as in this case here, 2, for example, it refers to character C. I know most people have no issue and no problem with modulo operations. So simple, like 15 mod 11, that's divided by 11, the result is 1, the remainder is 4, the result is 4. Now, sometimes people have a problem with the negative numbers, modulating negative number. As in this example, what's minus 80 mod 26? It's quite, difficult to calculate. But what you can do is ignore the operation and the signal, the sign, but then minus 3, what's the resultant of minus 3? There again, there are a number of ways to do it. The easiest way I've found, first on the negative line. Remember, I don't know if there's a new slide. Let me just see if I can get one of those Caesar's algorithm all the numbers. Oh, we didn't have them here. Let me get a table of numbers from 0 to 26, just from Caesar's. Instead of writing it now, it's a lot easier to actually just get a copy of it. Just give me a sec, please, guys. The lecture notes. Where did we have it? We had it in lecture number 4, symmetric encryption. Yeah, okay. There it is. I hope they'll come out complete. Yeah, okay. All right. Let's just look at this. If I say, for example, I will take an easy number, 28 modulo mod 26. How does it actually work? Usually, or what's modulo? Yeah, maybe 26. Yeah. So 28 in minus, that means you're going backward. If the number is say 28, as in positive 28, It's like you're going this way, 0, 1, 2, 3, all the way you get to 25. When you go around 26, 27, 28, and there's 28 is the number C. But if it's minus 28, you'll be going backward. You'll be going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 25, minus, minus 26, 27, 28, and that would be the number 23. So minusing is slightly different, but in minus, imagine, maybe that's just one quick, easy way to logically get it, is that imagine you're traveling in the opposite direction, and you end up with that number 24. So minus 28 mod 26 is 24. 80 mod 26 is 2. And that's based on are you traveling right or left? Okay, so from on the actual number. Another way to think of it or to remember it is you take that number if it's in minus, or let's say, how did this, the first number, how did 80? One way to look at 80 mod 26, how does it work? You subtract 26 from it once, and you subtract it again, and the third time, then you're left with 2, until you have a number less than 26. So that's really what we are doing. Every time we take 80 divided by 20 mod 26 is remove 26 from it once, remove it twice, remove it 3 times, and the third time we remove 26, we're left with 2, and that's the remainder. Now you can't take 26 out of 2 anymore, that's it. The other way around, if you have a negative number, one way to do it is add 26 to it with plus sign. So that's like subtraction, right? So you add 26, and then another 26, and another 26, and you're left with 24. You're left with 24. You'll add 24, that's it, less than 26, you stop at that, and that's what it is. You could do it another way. You can say, ignore the sign. That's another way of doing the minus modulo. Ignore the sign, do a normal sign, you get 2. Now put the sign back, so it's minus 2. Minus 2 is going backward. When you say minus 2, that means you go back this way. You go 1 step, 2. If you're here and I say minus 5, you go back this way, 1, 2, 3, 4, 5, that's V. If the remainder of the modulo is plus 5, like for example, I say, what's 31 mod 26? For example, it's 5, then it's 5 plus 5, that is. That's there it is, plus 5 going in this direction. If it was plus 31 mod 26. And if it's, come on. So it's 31 mod 26 equals 5. That's fine. If it's minus 31 mod 26, what you should do is first ignore the sign. So it's 31 mod 6 equals 5, but then put the sign back. So it's minus 5. So this is a quick way to do it. So what's, in this case here, if we are converting a character, what's 5? Plus 5 is starting from 0, you go 1, 2, 3, 4, 5, and it's F. So this is the letter F. What's minus 5? Starting from 0, you go backward, minus 1, 2, 3, 4, 5, and that's the letter B. Okay, I don't know if it makes sense, but that's a quick way of how to calculate the actual minus, the modulo in minus. So what's modulo 101 minus 101 mod 26? If it's in minus, keep adding plus 26 to it until you reach a number that's less than 26. And that would be the actual
Sorry.
value. Yeah.
I don't know if it's possible you go through the method with taking out the minus of, as in using the minus, the second one. I didn't really get that one.
The second one, ignore this sign. So
Yeah.
it becomes like plus 31 mod 6 is 5.
5, yeah.
And then just take that sign, put it behind the 5,
Exactly.
in front of the 5.
Oh, because in the previous example, I think we're meant to say 26 minus 5 again. Like when we got 2, you said 26 minus 2.
Okay, I don't know what you, okay. I don't know. Are you okay now with this or not?
No, I mean, yes, but like in the previous example, even after we got that's number 2, after we got remainder 2,
yeah,
we still took it from 26, but we didn't do the same thing for the previous example. That's why I'm confused.
Oh, okay. Well, okay. I don't know. Where is the 2? Is it here?
Yeah. We said plus 26 minus 2.
Oh, if maybe that's a different example. Oh, if.
Yeah, but I think it will
Okay,
give
if you
same
have a
result.
-2 at the end,
if it is -5, if you add in 26, that will give you 21. And same way you will get B also.
I don't know. I can't really hear you clearly. The last person who was speaking, yeah.
Can you add -5 to 26? You will get same result.
-5, yeah. If you add -5 to 26, you get -31.
No, you will get 21. Plus 26.
Oh, 21. Yeah,
5.
yeah. Okay, sorry. 26 minus 5. Yeah. Is it in this here? Is this what you're talking about?
Yeah, that's what I'm saying.
Yeah,
I think 26 minus 5, that should be 21.
Okay. Yeah. That's what -5 would be the equivalent of. Ultimately, it'll be 21. Yeah. But what I'm saying here, if you want to do it negatively, you have to go back 5 steps. If it's in negative values, so that's what -5 to the modulo 26. It's equivalent of 21. Okay, do you understand this? So ultimately, that's what we have to work out. There's no on the numbers here. There's no minus numbers, but when you do the modulo, it'll give you a minus number. But that minus number, which is -5, is the equivalent of 21. So, in fact, now ultimately, -31 mod 26 equals 21. Well, another way of doing it, you can say, right, okay, anytime you get a minus number, like -31, just add 26 to it. And keep adding 26 to it until you get a number. So this is -31 plus 26 is, what's it, -5. Now you stop at the -5. You keep adding -5 to 26 until you get a number that's between 0 and 26. And that's what, 21 positive, and that's where you stop. So if for example the number you want to work out is -78, you just keep adding 26s to it until you end up with a positive number. If the number that you're starting with is a minus number, keep adding +26, +26, +20 until you end up with a positive number, and that will be your final equivalent. That's one way of doing it. The other way is just, I'm saying, you can use whichever technique you find quicker and better. Ignore the minus. Let's say in this example, I said ignore the minus sign. Just do a normal 31 mod 26 with the remainder is 5. Now put the -5. What's the equivalent of -5 in the numbering between 0 and 26? let's add 26 to it once, and that'll give you the 21. Whichever way you find, if you have no issue with calculating the modulo in a minus number, use it, as long as it gives you the correct method. I've just shown you 2 ways of how to do it. We will be doing a lot of the minus modulo in the next few examples that we'll be using. So I just want to make sure you're okay with it. So for example, I have another example, minus 52 mod 26. You know, so what's that? And that's, if again, you can say, I'm going to add plus 26 to minus 52. That will leave you with minus 26. Add another plus 26, you get 0. You get a 0, that's the character A. You keep adding 26. Or you can do it another way, ignore the sign and mod it by 26. You get 2. In this case, the remainder is 0, that's it. Once you get any number between 0 or a positive number, you stop. Similarly, with this one here, minus 51. What's modulo of minus 51? You divide this, well, if you divide 51 by 26, or you add 26 to minus 51 algebraically, you'll stop at a certain point when you have the value 1. Or 51 divided by 26, ignore the sign, it's 1, and the remainder is 25 with minus 25. So once you have that, the last figure of minus 25, add 26 to it, and that will get you 1. Find any way that you find quick and easy, makes logic to you, and of course gives the correct result, and use it. I won't be asking you how did you do it. You just get the modulo for this number. You get a number minus 15 or minus 115. You need a calculator, guys. I hope you have a calculator with you, or if you have your mobile phone, get your calculator ready, and let's get moving. So who was asking me? Who was talking to me a minute ago? What's the minus 77? What's modulo 26 of the number minus 77? Hello? Good, I love the way. Oh, okay. So I'm assuming, hopefully, we have no issue with calculating the modulo. Modulo 26 or modulus 26 for a negative number. I know, of course, there's no problem with positive numbers, but also with negative number. So here's another example. Yeah, can you find out get me the value of what's minus 77 modulo 26? Can you please, guys, calculate it? Somebody come up with the answer.
Is it 1?
Minus 70. How did you get that? Minus 77. How did you get 1? Did you say 1 or minus 1? Sorry, I didn't hear.
1.
1. Okay. How did he get it?
77 minus 52 gives 25, and then 26 minus 25 is 1.
Okay, that's fine. And here's also another example of minus 66. You can do it also in many ways. You can keep adding 26 to minus 66 and give us 40. Add another plus 26. You get 14. Add another 26, and that'll get you 12. So, or you can divide, ignore the sign, the minus sign, 66. Ignore the sign, 66 modded or by 26. The answer is 2, and the remainder is 12. No, the remainder, I can't remember what the remainder is, for minus 14. Then what's minus 14? You add 26 to it and you get the answer 12. Okay. I'm hoping there's no issue. There's no problem. Now, let's get now to trying to work out the inverse. So the inverse of any number or for any matrix is what is that value that if you multiply it in this value, you'll get the identity. So what's the inverse of 2? It's 1 over 2. Why? Because 2 multiplied into 1 over 2 will give us number 1. This is in our own numerical system. With matrices, any matrix A, it has the inverse of A to the power of 1. It's inverse matrix. If you multiply them into one another, you get the identity matrix. Remember the identity matrix? It has the value 1s along diagonally, and the rest of it is 0s. And usually also the identity matrix, if you multiply it into any matrix, it will not change it. But any two matrices, one the inverse of the other, you multiply them into one another, you get the identity matrix. Same as our digital numbers or ordinary numerical system. Any number you get 7, multiplied into its inverse 1 over 7, the result is 1. So back again, the modular inverse of any matrix. If we have any matrix and we multiply it into its inverse, it'll give us a number. If we want to calculate that to the modular value, a particular value, the modular of, say, of m, let's say m is 26, the modular of 26, the result should be 1. So even if the matrix are not within the modulus, but if we calculate the modulus, it will always be equivalent to 1. For modular inverse, A and M must not have any prime factors in common. So we'll look at that now in a minute. So these are the modular inverses for number 26. What do you mean here? Find, for example, if we try to find the modular inverse of 9 for mod 26. What's the inverse of 9 within the numbers of 0 to 25? That's the modulus 26. The determinant must be an odd number between 1 and 25. And this is just a general rule. We'll see later on why you can actually physically calculate to create this table. Every number has a modular inverse. What do we mean by the modular inverse? Modular 26. It can be done to any modular, but let's just concentrate on 26. So any number has a modular inverse within the range of 26. If we multiply those two numbers together and mod it by 26, if the remainder is 1, then that's the inverse of that number. So for example, what's the inverse of 9? Well, you can multiply 9 times 1 is 9, mod it by 26. Does it give us the result 1? If it does, then that's fine. Multiply it into 2. 9 times 2 is 18. 18 divided by 26, the remainder is 18. It's not 1. 9 times 3 is 27. Mod by 26, yeah, the division is 1, but the remainder is 1, and that's how we find out. So we say 3 is the inverse of 9 if we're talking about the modular 26. Only within the scope of modular 26, 3 is the inverse of 9, and also 9 is the inverse of 3. For example, what's the inverse of 15? You have to take it. 15 times 1 is 15, mod by 6, remainder 15. 15 by 2, so that's not an inverse. You multiply into 2, 15 times 2 is 30, mod 26 is 4, the remainder is not 1. Then 2 is not the inverse of 15. 15 times 3 is 45, mod by 26, the remainder is not 1, until you get to multiply it into 7. you multiply 15 times 7 and divide it by 26, you get a remainder of 1. And therefore, we say 7 is the inverse of 15 for modulo 26. So it's important to get the modular inverse for any, for you know, a number. So usually the determinant. So it's easier to do it. It's a long process, but you know, we do it once or twice and it should be okay. So this technique was done by some mathematician. His name is Hill. So this is called the Hill cipher. Hill cipher uses matrix with a modulus, and we're going to now concentrate on modulus 26. And so it takes the message, convert it into numbers from 0 to 26, the characters, and then take a block of characters based on the matrix. If the matrix 2 by 2, then we take 2 characters at a time. If it's 3 by 3, then we take 3 characters at a time, and so on. And we multiply it, and it'll give us another characters that we can send them. And the characters have to be less than the number 26. So they get converted into English characters as well. And then to actually decipher that message, we have to find out the inverse of that matrix and use it to multiply it into the ciphered message, and bring back the message. So that's really the basic idea. So now we look at one matrix, we use it to encrypt, and we have to calculate the inverse of this matrix and use it to decrypt. But not any inverse, guys. It has to be the inverse within modulo 26. So we'll always use mod 26 because we're using the English language. If our alphabet is more than 26 characters, we'll go for bigger modulos. So how do we actually work the modularly inverse matrices, or how do we modularly inverse a matrix to a particular number? Make sure that all values on the modulo are less than 26. So if there is any bigger number, we modulate it. We take the modulo. Calculate the determinant of the first matrix. So we get the determinant. This is in order to get the inverse of a matrix. First, find its inverse. Make sure the determinant has a modular inverse for mod 26. So if I give you a matrix and say, find the inverse of this matrix in modulo 26, first, you find its determinant and look at this table. Can you actually, does it have an inverse? Like, for example, you got number, I don't know, 2. So no, if you get modulo 2, there's no inverse for it. So it has to be a number. The determinant has to be odd number and between obviously 1 and 25, except number 13. If the determinant is not odd number or if it's 13, then there's no modular inverse for this matrix. We cannot use it. We can use it to encrypt, but we'll never be able to decrypt the values because there's no inverse modulo 26 inverse for this matrix. And then calculate, like now you have a matrix, you got the determinant. We know how to get the determinant, especially if it's 2 by 2, multiply each 2 values, diagonally and subtract them, and that should give us the determinant. And then formulate the adjugate of that matrix and multiply the modular inverse into it. So this is pretty much what we did last week. Find a matrix, get its determinant, get the adjugate of that and multiply the determinant into it, and that should be the actual inverse, except now for everything is going to be according to modulus 26. Again, it's easier to do it than to talk about it. So let's go ahead and do it and use it to encrypt and find the inverse and use it to decrypt and make sure it works. And of course, once you get the determinant, first you get the inverse, make sure that you have the correct inverse. Prove that it is the right inverse. How do you prove it? You multiply the matrix into its inverse, and we should get the identity matrix. So it's pretty much, well, it's a lot easier than what we did last week, but everything is done according to modulo 26. So every matrix, if it has bigger numbers than 26, mod it. If the inverse or the determinant, if the adjacent matrix or the inverse matrix has bigger numbers or negative numbers outside the range of 0 to 25, any number bigger than 25 or smaller than 0, you have to mod it. If it has negative number, we don't have in the modulo, we don't have negative numbers. All numbers in a matrix have to be between 0 and 25. So if it has, we have to correct it to mod 26 and carry on. Then once we do that, then everything goes to, it will work. Okay, so if the determinant is not one of those values, then the matrix has no modular inverse. So this is the point. We give you a matrix and say, use this matrix to encrypt a message. First thing, do a quick calculation of the determinant. If that matrix had a determinant that's not 1 or 3 or 5 or 7, one of those numbers, then you say that's of no good. There is no inverse to this matrix, and therefore we shouldn't really be using it to encrypt, because you cannot decrypt the message. Because a number and its inverse must not have any prime factors in common. How do we, okay, so we've already worked out that there's only one value. Usually they should be prime numbers or relatively prime. So even if, say, number 9 is now prime or 15 is not prime, but within 26 it is. It doesn't divide by any number. See, modulo 26, all these numbers here are what they called relative primes to 26. That means they are prime numbers. They don't have 26 and 3 don't have any other common number that they both divide in other than 3. Same with 19. 19 is prime anyway in 17. But 21 is not, normally it's not a prime number. It divides by 3 and by 7. But with with 26, the number 26 does not divide by 3 and 7, and therefore doesn't have any common divisors with the number 26. So these numbers are considered prime numbers to 26. That's the main point, that they are acceptable. And all the other numbers are not accepted, like 2, 4, and all that. They have, other common values that divisible with 26. All the even numbers and the number 13, they actually divide into 26 somehow. But these numbers do not. And that's why they are. And you can find out, what's 17 modded by what number is multiplied into 17 that will mod to 26, give the value 1, and that's 23. So here we have every pair of numbers, like the modulo. If we have a matrix A, it has a determinant 5, then its inverse will have 21. See here on the table here. So once we have the original matrix, in order to calculate the inverse, its inverse, you need to calculate its determinant. But the determinant for its modulo inverse is outlined here. So if you get our matrix and it has determinant 5, then the determinant for its inverse is 21, and so on. If it has determinant 15, then the determinant for its inverse is 7. So this table is important. You can calculate it, or you can memorize it, or whatever way you can do it. But let's take an example. It's easier to work an example. Find the modular 26 modular inverse of this matrix A and prove that it is its correct inverse. So basically, what's the inverse for this matrix, but based on modulo 26? So all values in the matrix must be between 0 and 25 to do the modulo 26. Oh, this is a different example. Find the 26 modulo inverse of this key matrix, 5, 8, minus 9, 3. So first thing, get rid of the minus 9. What's a minus 9? So this matrix here is pretty much the same as this matrix with mod 26. So if we take this matrix, mod it by 26, 17 mod 26, we can get minus 9, or minus 9 modded by 26, 17. So pretty much we didn't change the matrix, even though, but we got rid of the minus signs. Either the value is minus, we get rid of it, or if any of the values is bigger than 26, we can only use, like, we have to convert to modulo 26. So all the numbers within a matrix, they must range between 0 and 25. If there are bigger numbers than 25 or less numbers than 0, mod it. So that's the first step, and it's an easy step. And that's why it's important to know how to calculate the modulo of a minus number. So, and the easiest way, if the number obviously is not very, very big, is just to add plus 26 to it. And you see, and if it, for example, it's minus 49, you add 1, or 55, you add 26 to it, and then still big, you add another 26 to it, and add another 26, and whatever is left, then a number less than 26. So as long as it's negative number, keep adding minus 26. Anyway, I won't talk about it anymore, because you can, hopefully you have no issue with doing it. There are 2 or 3 ways to do it. Find out the best way that, the quickest way you can do it. So the modulo of 26 for number minus 9 is number 17. If you still don't know how it worked out, let me know later. Okay, now find the determinant and its multiplicative inverse. That's the other, and its inverse basically. So how do you find out the determinant? We've done it before. We've done it last week. You multiply these two numbers together, 5 times 3 minus the multiplication of those two numbers together. So 5 times 3 minus 17 times 8, and that's, I don't know, that's whatever, 100 minus 121. Okay, but that number is too big. It's bigger than 26 or outside the range of 0 to 26. What's the modulus, 26 modulo of this number? So it's minus 121 mod 26, and that give us 26, give us 9. So I don't know, whatever way you calculate it. So minus 121 mod 26 is number 9. So this determinant of this matrix is 9. So obviously the original determinant is minus 121, but because we are dealing with mod 26, everything, see, with the original matrix, any number, if the matrix has any number bigger than 26 or outside the 0, it's a negative number, then convert it into modulus 26 and find the determinant. The determinant is very easy to calculate if it's 2 by 2 or even 3 by 3. But if that number is bigger again than 26 or less than a 0, then mod it. And now we find the determinant. This is the determinant, the modular determinant for this matrix, for the original matrix. Now we want to create the inverse of that matrix. So we have to find the determinant of the inverse matrix. That's when we look at the table. Remember the table? Of course, you can calculate it yourself. What is the inverse of this number? The determinant, it's whatever number you multiply it into 1 mod 26, into 2, into 3, into 4, and whatever the mod equals 1, then that's the inverse of this determinant. But if you have the table, I'm going to go back or forward to back to the table, and here's the table, and it says 9. Here's 9. Its inverse is 3. modular inverse. Okay, because it's correct, because 9 times 3 is 27. 27 divided by 26 gives us the modulo, get the remainder 1. So the inverse of this determinant, we got the determinant for the original matrix is 9. Its inverse to modulo 6. So the determinant of the new matrix, the inverse matrix, is 3. So let's go back. So this way we got so far. This is our original matrix. That's a matrix we're going to be using for encryption, maybe. And we want to find out the inverse of this matrix. We first find its determinant. We found this determinant, but no, we want its modulo 26 determinant. We found the modulo. We go now and find out the inverse of its, oh, sorry, the determinant inverse of 9. So the matrix can have an inverse if the determinant is odd, which is 9. This is odd. If the determinant is greater than 0 and less than 26, 9 is greater than 0 and less than 26, and it's not 13. Because 13 divides into 26. It's not, it has to be relatively prime with the 26. So 9 is perfect. It doesn't divide in 26. It doesn't have common divisors by 26. 9 is not a prime by itself, but it divides by 3. But 26 does not divide by 3, so they're okay. All right. So, and that's where we got it from this table. So now we know the inverse matrix is going to have a determinant 3. So how do we work out the actual inverse matrix? We go to our original matrix, we take the adjacent matrix and multiply it into 3, and that will be our inverse matrix. So find the adjacent matrix. What's the adjacent matrix of, this is our kind of original modular 26 matrix. That's our, so we have now, we are going to create the inverse. Sorry, we take the adjacent inverse of this matrix, the adjacent of this matrix, and multiply it into number 3. So what's the adjacent? Anybody remembers how to get the adjacent matrix? Reverse these two numbers, 5 and 3, make them 3 and 5. And these numbers, leave them where they are, but reverse their signs. So their signs go -8 and -17. That's the adjacent. That's the first step of finding the inverse of a matrix. Get the adjacent matrix and multiply it into its determinant. We know we already worked out the determinant for this one is 3. The determinant for this one is 9. That's our original matrix, and it has determinant 9. This is its adjacent, and its determinant is 3. If we multiply 3 into this matrix, we'll get the inverse of that matrix. Okay, does it make sense, guys? So yeah, hopefully. Okay, finally, this is the last step to find the inverse of that matrix. So we take the determinant that we've already worked out for the new inverse matrix. It's a modular 26 determinant, and multiply it into the original, into the adjacent matrix, which is 3 -8 -7 and all that. And we work out, you can do it either way. You can first calculate, when we got this, we could have here worked out, oh, let's get the mod 26 to this one. We could have done that. So we get the adjacent modulus of this matrix, right? Because this one has numbers that are, outside 0 to 25. But in this example, we carried on and we took the determinant and multiplied it into every value. Now, the final process, this saves us because we could have done it twice. This way, we only do it once. Multiply this number into every value. And now this has numbers either bigger than 26 or less than 0. So we end up modding it with 26. So how do you actually mod? Okay, there's somebody there. Maybe I should silence everybody. or was that me? Okay, never mind. So 9 modded, 9 modded by 26 is 9, and 15. So these two numbers between 0 and 25, they don't change. But this one, minus 24 mod 26, is one way to do it, is just add plus 26 to it, and the remainder is 2, or whatever way you find is easy. I find just add 26 to it. Keep adding 26 until the number is suitable and use it. Same with this one here, 51. 51 added to 20, mod it by 26. It's actually, if you do the division, 51 divided by 26, the remainder is 25 in minus. But what's 25 in minus? You add the 26 to it, and that gives us 1. So this is now the inverse matrix, the modulus inverse matrix of our original matrix. This is the one that will encrypt or decrypt. So if our original matrix was used to encrypt any message, this is the one that will decrypt it. And not our original matrix, it's this matrix here. Even our original matrix had a minus number, so this is the modulo of our matrix. So this matrix is used to encrypt any information, 5, 8, 17, 3. This is the matrix that will decrypt that message. Okay, so this is it. This is Hill cipher. So shall we use it? Maybe, I don't know if, I hope we have an example of it. So that's the original matrix we started with. We converted it into modulo. This is same matrix as that, but this is corrected to modulo 26. And this is the inverse, the modular inverse of this matrix. Remember, everything now is modular 26 inverse. So now this is the matrix we can use to encrypt or decrypt. But if this matrix is used to encrypt, that matrix is used to decrypt. And we should have an example. Here's an, I hope we have, no, right. Before we get an encryption decryption example, how do we know, how sure are we that this matrix and that matrix are the inverse of one another? How do we know this is the inverse matrix of that? If anytime, like especially in the exam, if you do, even if you are not asked to prove it, make sure do it, just to show, to make sure that you have the correct solution. Sometimes you can make one mistake, and instead of 2 here, you have 3, and you think you got the inverse, and that's not the inverse. But to be certain, how do you know this is really the inverse of that, or they are the inverse of one another? Then this is the proof. How certain are we? Well, simple. Let's multiply them, and if we get this matrix, then that's the right. It is. They are the inverse of one another. This is the matrix that should come out of multiplying 2 matrices that are one of the inverse of the other. This is called the identity matrix. This is like in our numerical system, number 1. So if you multiply 8 into 1 over 8, the result is 1. 9 multiplied into 1 over 9, that's the inverse, then the result is 1. In matrices, any 2 inverse matrices, one is the inverse of the other, then if you get this, then that's they are the inverse of one another. So let's multiply these. How do you actually multiply these 2 matrices? They are square matrices, 2 by 2, so then there's no issue multiplying the 2 of them together. Remember, you can't always multiply, and not every 2 matrices that you multiply A into B, B into A would not give you the same result in matrix operations. But if they were inverse, then they would be. So 5 times 9, so you multiply this line, this row into this column. 5 times 9 is 45 plus 8, 45 plus 8 is 53. Now multiply this row into this column. 5 times 2 is 10, and 8 times 15, I don't know what 8 times 15 is, 8 times 10 is 80, 40, 120, and 10 is 130. There is the result, that's correct so far. And then this row into this column, and they give us this value here, and then 17 times 2 and 3 times 15. It gives this value. Now let's mod these to 26. So 53 mod 26, you divide by 26 is 2. 2 times 26 is 52. The remainder is 1. That's what goes there. 130 divided by 26, it divides without any remainder. Okay, so it's 2, 4, 5. It's 130 divided by 6, the result is 5, the remainder is 0. That's what it is. And 156 again divided by 26, the result is 6 and the remainder is 0. And 79 divided by 26 is actually 3, and 3 times 26 is 78, the remainder is 1. And that's the identity matrix. So this is a proof that this and this, those two matrices are the inverse of one another. Now we've proved that they are the inverse of one another. Let's use them to encrypt and decrypt. I hope that's the next example. Oh, what happened here? Slideshow, yeah, from here. Don't tell me this is the end. Okay, there should be a good example. Maybe I used the wrong slides. Hopefully not. Okay, let me open the correct screen sharing has stopped. Okay. There should be an example of actually, yeah. I was using the wrong slide. Well, up to this point, there's no issue at all. So let's go. Right, am I sharing now? I just need to be, let me make sure we are sharing the correct slide. Let me close the previous one. First, let me make sure it is the right one. No, they all end up at that point. On a momento. MSc lecture notes. No, they're pretty much the same. Quick. Okay, so let's, here it is. Let's have a couple of examples now to try this out, make sure we're clear on that. Let me share this. Sorry. Yeah, but, doesn't seem to be, I can't find the actual, I have the file open, but when I want to share it, it doesn't, I can't find it. So I'll stop sharing again, share again. Maybe too many files open. Just again, give me a moment. Show all windows. Yeah, there it is. Okay, can you see the Word document open?
Yes.
Hello? Yeah, okay, great. So this is the one that has the example. So let's have an example and do the actual ciphering example here. Let's take this one here, the ciphered message. Yeah, let's take this example here. This is the message we want to send. Of course, the message can be much longer, but let's just say we have, oh, this was ciphered. Actually, this message was encrypted. A message was encrypted, and we got this one as a ciphered message. This ciphered message was produced after ciphering plain text message with Hill cipher using this matrix. So this matrix was the one that was used for encryption. So let's work out, let's decipher this message. So let me go down to the example. So to decipher this message, first thing, we need to work out the inverse of this matrix. Okay. In order to work out the inverse of this matrix, we need to work out the inverse of this. First, we need to find out what's the determinant for this matrix and get the conjugate matrix and multiply and find the inverse of this, the determinant, the inverse determinant first. So for this original matrix that was used for encryption, it has, let's find out its determinant. And its determinant is 2 times 2. Can you see? Can I make this a little bit bigger? Yeah, see if this is okay. Is this okay? Yeah, hope you can see it. Okay, guys, so let's go through it quick without me talking too much. And then if there's an issue that's not clear, just stop me when you feel. Like, first step is to find out of the original matrix, what's its determinant. So its determinant is, this is a 2 by 2 matrix. Its determinant is 2 times 2 minus 5 times 5. So 4 minus 25 is minus 21. Modding minus 21 gives us 5. So this is the modular determinant for the original matrix. It's 5. Now because it's odd because it's not 13, because it's between 1 and 25, then it's okay. This matrix has an inverse. We know that. Okay, so that's the first thing. Is this a good determinant? It tells you that this matrix has an inverse matrix or it has no inverse matrix. So sometimes you might say, okay, I'm going to try any matrix, and you put any numbers here, and you have a matrix and you encrypt a message. But if you cannot make sure that matrix you can have an inverse for that matrix. How do you know? You find out its determinant, and if it's determinant, if it's an even number, then it has no matrix and no inverse. It has to be an odd number that is relatively prime with 26. That means it does not have any common divisors with number 26. So it has to be an odd number between 1 and 25, and excluding number 13. Okay, so that's the determinant. Again, I talk too much. Right, so let's go. This is the determinant. We want to work out the inverse determinant for that one. If you look at the table, there it is. 5 is its inverse determinant is 21. How do you know? If you multiply 5 into 21 and multiply by 26, 5 times 21 is 105, right? If you divide that by 26, they divide 4, I think, the result, and the remainder is 1. That's fine. That's exactly 21 is the determinant inverse of 21. Now we have the determinant. All we need is the adjacent matrix of 2552. What's the adjacent matrix? You reverse these two numbers. 2 and 2 are reversed, and you change the sign of those two numbers. That's the adjacent matrix. Now all we have to do is multiply that number, which is 21, into it. It's determinant. So it's 21 multiplied into the adjacent matrix. So 21 times 2 is 42. 21 times minus 5 is 105. Oh, it has big numbers, bigger than 26 and less than 0. Then we have to modulate them to 26. So modded by 26, so 42 modded by 26. Like 42 divided by 26 is 1, and the remainder is 16. That's fine. Minus 105 modded by 26 is the result is plus 25. Same here. So this is now the new matrix. That's the inverse of that matrix. Well, of 2552. So here are the two matrices. One, the inverse of the other. How do we know they are the inverse of the other? Let's multiply them, and we should get the identity matrix. Gloria, are you all right? Are you watching?
Yes,
I can see you're looking
here.
outside your window out there. You're not with me.
I'm here. Take note.
Okay, so let's multiply this one into this one. So this row into this column, 2 times 16 is 32, plus 5 times 25 is 125, and the first value. Second value of this row into this column, 2 times 25 is 50, and 5 times 16 is 80. So ultimately, this one multiplied into that one, if you multiply by 26, I don't know what the value is, but I'm sure at this stage it is. So if you mod these numbers by 26, you'll find that they come up to 1001. So these two are okay. They are the inverse of one another. So now we worked out the modulo inverse of this matrix. It's not the inverse, it's the inverse based on modulo 26. So now let's use it to decipher the message. The message is IJTP. That's a ciphered message. We want to decipher it. If you have 2 by 2 matrix, you take your message 2 characters at a time. So you decipher AJ on its own. If our matrix is 3 by 3, then you take 3 characters. If it's 4 by 4, so how many characters you take depends on how big the matrix was used. Of course, the bigger the matrix, the more secure it is. But we just want to prove the idea, so we'll work out now with 2 by 2 matrix. So IJTP, we'll convert them into numerical values. What are the numerical values of those? So the numbers are numbered, or the numbers are between 0 and 25, A to Z. So this is the actual grid that we'll be using. So the message we want to decipher is IJTP. There it is. So we convert IJTP. I is 8, J is 9, T is 19, and P is 15. So we take the first two, I and J, we multiply them into the inverse matrix. Our inverse matrix is 16, 25, 25, 16, multiplied by into I and J, which is, so I'll put down here I, just so you'd know that's why we're using 8 and J, and there it is. But forget about the I and J. So now 16 times 8 plus 25 times 9 is 358. The second value is multiply the second row by this column. 25 times 8 plus 16 times 9 is 344. Okay, these numbers are way too big. Mod them to 26. If you divide 358 by 26, whatever the number is, it's, I don't know, it's probably 7 or 8. And the remainder is 15. And this one, the remainder is 6. 15, there it is at the top there. 15 is the character P, and 6 is the character G. So I was the cipher for P, and J was the original message is G. So the next, we take the next two characters, which are T and P. T is 19 and P is 15, multiply into the inverse message matrix. So 16 times 19 plus 25 times 15, that's 679. And if you mod that by 26, you get 3. 3 is the actual, what's that? 0, 1, 2, 3. 3 is D. And so on. So the next row is 2516 times 1925, 715 multiplied by 16, it's 13, and 13 is the letter N according to the grid here. So 13 is the letter N. So this message, IJTP, was an encryption of the plain text message BGDN. I don't know if PGDN makes any sense to anybody. Anybody knows what BGD stands for? Don't worry. But that's the original plain text message. It actually stands for Postgraduate Diploma in Networks or in Computing, if we had to see. But it could have been any other number. Is that okay, guys?
Yes.
Okay, good. So maybe we'll have an example, and maybe you can work out something for me.
Sorry, sir. Is this particular Word document on the module?
No, this is an example. I'll include that as an example.
So that if you want to practice later on, you could just use it also.
Yeah. No, I think we'll probably practice it right now, in fact. Okay, so here's an example. Maybe let's practice this one. Okay, here's a ciphered message, guys, in ACU, and I'd like you to work it out. So let's do this and take a break after this one. But I'd like each of you to work it out. Like, don't leave until you work it out. And I'm here to support you. So can you start? If you look at at the document, you should get the steps. maybe I can, if you take this matrix and the ciphered message in ACU, then we can remove this and go back to the actual steps involved. So first thing, so the first step is to find out if first this matrix has everything in, but it's a modulo 26, so there's no issue here. We don't have to modify or mod this matrix. So this matrix is already a modulo 26 matrix. To get the inverse of this one, you need to first get its determinant and then convert the determinant to the inverse determinant, and then get the adjective of this matrix and multiply the inverse determinant into the adjective in order to find the actual reverse or inverse matrix. So first thing, find out what's the first step, find out what's the modulo determinant for this matrix. Okay. So who was the last person talking? Was it Aluwatu Bibabata? Is that you? Guys, let me also remind you of something else that I'll send you an email anyway, but I think we missed a lecture. Did we miss a lecture on the 17th of March? On the St. Patrick's holidays. I think that's what it was, Wednesday. Yeah, 2 weeks ago we missed a lecture. So we will replace it. We will replace that lecture next Wednesday. So next Wednesday, even though it's assignment week, but you'll have to come up for that lecture. We need to make up for the missed lecture. And the only time we can make it up is next Wednesday. So next Wednesday, please remember that we have a lecture. I won't keep you for the full length of the lecture time, but you'll need to come up. I'll send you an email, but this is just to let you know, those of you who are here. Okay. So who's gonna help me? Who got the actual determinant for this matrix? Nobody wants to talk to me. Jose Carlos Rivera, are you there?
Yes, I'm here.
Good morning to you.
Good morning, sir.
How did it? Yeah, go on.
I got -9 as a determinant.
So it's, how did you get -9?
So it's 3 plus multiplied by 5
Yeah,
minus
15.
4 multiplied by 6.
Yeah, so that's -9.
Yeah.
But we need to get the modulo value for that -9. What's the modulus for -9? The modulo 26 determinant. If you get a minus number or a bigger number than 25, then you have to mod it to 26.
Mm-hmm.
What's -9 modulo 26? You just keep adding. If you get any negative number and you want to calculate the modulo for it, modulo 26, just keep adding 26 to it until you have a positive number. So -9, yeah, so plus 26 is 15. So the modulo for this, the determinant modulo for this one is 15. Now we want, once you get that, that's the first step. Now you want to get the determinant for the inverse matrix. What's the inverse determinant for 15? You need to go
It's
to that
17,
table.
sir.
Was it 17? 3 times 5 is 15 minus 24. It's
Yeah.
minus 9.
Yeah, it's 17.
Okay, sorry. So 17, good. Okay. I knew it was 17. I was just testing to see if anybody was listening. Okay, so it's 17. So now we have to go to the table and find out what's the modulo inverse of 17. What's the determinant that we're going to use for the inverse matrix? And what's 17 is good. It's positive. It's odd number. It's between 1 and 25. So this matrix that in front of us actually has an inverse. All we need to know is its determinant, the determinant of the inverse matrix. And what's that figure you found? What's the inverse of 17?
23.
23.
23. Jose doesn't seem to be on top of the thing. Are you there, Jose?
Yes, yes.
Did you find that 23 is the modular inverse of 17?
17. Yeah.
From that table. And the reason is if you multiply 17 times 23 and multiply 26, the remainder is 1. Okay, so 17 and 23. Okay, all right, so these are the inverse. Now we need to find out the inverse, the adjacent matrix of this, of A.
Mm-hmm.
Again, Jose, what's the adjacent matrix for this matrix here? The one in front of us now.
Okay.
To find out the adjacent matrix, you reverse these two numbers, swap these two numbers, like 3 and 5. You make them 5 at the top and 3 here on the bottom right. And these two numbers, 4 and 6, leave them where they are and change their signs. So they both have positive signs. Now they're going to have negative signs. So the adjacent matrix is 5 minus 6 minus 4, 3.
3.
And you multiply it into the new determinant, which is 23, and that will give us the new inverse matrix. Okay, Jose?
Yeah.
Good. So
I multiplied by 23. It's 69.
Okay.
138.
Okay. Very
92.
good.
92.
Okay. Now you need to. That matrix is not at a mod 26 matrix. You need to mod it to 26. Reduce it to 26. So divide every number by 26 and get its remainder. And that's going to be your inverse matrix.
Okay, so 17 for the first one.
I hope so. Okay, give me the first two numbers.
8, 17 and 8.
Yeah. Okay, I don't know how correct this was. Yeah. Why do I have 6 and 4? Oh yeah, 6 and 4 are correct. So 23 multiplied into, so did you say 115 and a minus 138? I have now,
yeah,
in minus. So if you mod that by 26, it turns out into 11, 18, 12, and 17. Do you get that, or you're nearly near there? See, sometimes it's a little.
Yeah. Yeah, I got around the minus.
Okay, you have to be careful with that minus thing. Find a way of how to quickly calculate minimized number modded by 26. The way I do it, I ignore the sign first. There are 3 steps. Ignore the sign, work it normally. Just in this case, 138 mod 26. I don't know, what number do you get? What number do you get? I think you get something like 8, right?
Yeah.
Or something like that. Then put the sign in front of 8. So you have -8. Add another 26 to it. So that's step number 2. Add another 26 to -8, and that gives you 18. And that's the actual. That's how I do it. There are actually many ways to do it. This is the quickest way I found to do it. Forget about the sign. Mod it normally by 26. Whatever number I get, I put the sign there on it. That's -8. And I do one last step. I add another 26 to it. And that makes it 18. Try it or see whatever other way. If your calculator gives the right stuff, okay. You know, in the exam, you will need to do this. You'll need to find the modulo of -138. If you have a calculator that when you do it, it gives you the correct number. If your mobile phone does it, you know, whatever calculator, you are allowed to use a calculator. So make sure you know how to use the calculator, or else do it manually. I do it manually. I look at the sign number, forget about the minus, and do a normal mod and add 26 at the end to it. I will put the sign later on onto the result and add one last time. I add another 26 to it in plus 26, and that usually works for me. If it works for you, find out a way that will work for you, or use your calculator. Okay. Is it time for a break? I think maybe we take an early break. Yeah.
Yes, it is.
And come back later. Yeah. Yeah. Okay. Because we just finished the Hill cipher. We can have maybe another example, and you should be all right on that. And it's a definite exam question. So make sure you know how to encrypt or decrypt using Hill cipher with modular 26. Right? It's all like it's almost a definite exam question. Right. Remember, okay, now we got this. Is everybody else okay, guys? Anybody's having any problem or issue or any question at all on how to do the Hill cipher? Okay, so once yeah, go on.
Yeah, the major issue I'm having is when the number is greater than 26. I'm not really understanding how you are returning, how you are getting the modular value of it.
Okay, see this 115?
Yes.
If the number is, this matrix here is outside the modulo 26. So we need to bring all the numbers to be to modulo 26.
No,
so
I understand this one of bringing this one, but when is the determinant? Is it the same method that we use here to find the inverse that is 11 that we use to get the, like if the determinant of, that we calculate the determinant of a...
The determinant of A is worked out as 17. There, this is the determinant for this example. Here's the matrix. Its determinant is 3 times 5 minus 4 times 6. You multiply these two numbers together and these two numbers together. So 3 times 5 minus 4 times 6. That's 15 minus 24 minus 9.
Yeah, I'm
because
saying
the
that
number, yeah.
What I'm saying is that this one is easy to do. All you just need to do is add 26 to it, and you get your modular, the mod of what is supposed to be basically. Then,
yeah. To find -9 is not, is outside 0 to 25. Then we need to get divide. Yeah, we get the modulo. So and to get the modulo means give me the remainder, divide by this number and get me the remainder. If you know how to divide a negative number by the remainder, or if your calculator can do it for you, that's fine. The result is 17. If you don't have the calculator, or your calculator doesn't, you tried a couple of times, it doesn't give you the right result, how do you actually get it? There are many ways. You can look at the numbers, the numbering system, the grid, and go backward. See, when the modding is going forward, if I say what's 28, you go 0, 1, 2, 3, 4. When you get to 26, 25, you go back to 0, 1, 2, 3. You just keep. It's like you're going around in circles. The numbers, For example, in our timing system, we mod it by 12. Let's say what's time. If I say time now is 1400 hours, 14. So you go down 0, 1, 2, 3, 4, 5. And when you get to the 12, you go back to, back to 1, 2, 3 again. And you go, but you keep counting. And if I say it's -2, you have to go, just going back in reverse. Hold on, do we have the actual numbering? Do we have a grid here? I don't have a grid here. Oh, no. Here's the grid. So if I say to you, for example, what's 28 mod 26? There's the way you go. You go 0, 1, 2, 3, until you keep going until you reach number 28. This is one way of doing it. You say 21, 22, 23, 24, 25, 26. You go there, the 0 becomes 26, 27, 28. So 28 and 2, they fall together. So that's what 28 mod 26. It's you divide, if you want to do it mathematically, divide 28 divided by 26. The result is 1, and the remainder is 2. And there it is, 2. So 28 is the equivalent of 2. Okay. But also if you go 29, 23, 12, until you get the number 51, 50, 51. What's 52? There's no 52. You go back again to 0 again. So 52 is 0. 53 is 1. Maybe 54 is 2. So 54 is the same as 28, is same as 2 in modular 26.
Okay, thank you very much.
Okay, so, but most calculators will have this mod operation. If not, you'll have to do, if not, what you should do, let's say 117 mod by mod 26, and you have a calculator that doesn't have the mod calculation, the mod operation. So you just do a divide. Let's say 110 divided by 26. You'll probably get the result 4 point something. Just take the 4 and multiply 4 times 26, and that's 104. Now subtract your original number 110 from 104, and the remainder is 6, and that's what it is. Okay, I don't know. See, it should be easy enough, but okay. The other one, the problem is when you are doing a negative number. So what's -5? -5. So remember, you're always at this starting at this point 0. If the number is positive, +5 is there, F. But what's -5? -5 is going backward, back this way, 1, 2, 3, 4, 5. So -5 is same as +21. Okay? So if I say to you, what's -8? Starting from 0, you go back 1, 2, -1, 2, 3, 4, 5, 6, 7, 8, going back 8 steps in the opposite direction. So -8 is same as 18. But if you don't want to be counting backward, well, a quick mathematical way, if I say, what's -8? I'd say to you, take -8, add to it 26, plus 26. So plus 26 minus 8 is 18, and that's what it is. So it's a good way just to keep adding plus 26 to your negative numbers. But if your calculator can do it for you, that's great. But if your calculator isn't there or doesn't work, just add plus 26 to it, and that's exactly like modding it by 26. But the problem is if the number is -300, so you have to add 26 and add another 26 and add another 26 until you get a positive number. So it can take a long time. So find out a quicker way, the best way to do it. The way I do it, I ignore the minus sign. I say if it's a big number like 300, Instead of minus 300, just deal with 300. 300 mod by 26, whatever it is. The number, let's say it says to me, it's 2. Now I put minus sign beside it, and then add one more time 26 to it, minus 2 plus 26, 24. And that is the actual correct solution or answer to a mod with a minus number. So if the number is small, like -5, -7, okay, just add 26 to it and the answer is going to be correct. So if I say to you -10, what's -10? What number would be -10 mod 26? Who was talking to me? Who was I talking to?
No,
What's -10 mod 26?
yeah, I think it should be 16.
Yeah, you just add plus 26 to it, -10, that's plus 16, and that's the letter exactly. So if it's the number is small, just add 26 to it. And if just adding 26 doesn't work, add another 26, you know. So sometimes the number is, I don't know, 55. So add 26 and add another 26. That's, you know, 52, basically, add to 52. So if it's -56, you add to it 26 twice, that's plus 52, and that gives you a remainder of 4. And that's what the result
But
is.
if the determinant is not in that, if we get the determinant, the determinant, and is not in that table, we know that.
Oh yeah, that's another thing. Yeah, if the original matrix, here's this matrix, if it has a determinant that's not an odd number between 1 and 25, not including 13. 13 is an odd number, and it's between 1 and 25. But 13 also has a common denominator with or divisor with 26. 13 doesn't work, but every other number is okay. If it doesn't have a number, either 1, 3, 5, 7, 9, 11, and then skip 13, all the odd numbers up to 25. If it doesn't have one of those numbers, then you can say, safely say, this matrix does not have an inverse.
Okay, thank you.
Okay, okay. Okay, guys, let's go for a break and come back. Take care. I'll see you in half an hour max, okay?
Okay.